Gentlemen, I think some people are still drifting in. I understand that the session just before this ran over a little bit, but we're going to start, and I want to say at the very beginning that you are in for just a wonderful, wonderful treat with our speaker here tonight. My name is Mary Snitch, and I'm the VP-elect for Public Policy, and I'll move into the full position in May. And I'm also tonight in the privilege of recognizing and introducing our speaker. I'm representing Lockheed Martin and Dr. Ray Johnson, who is the executive chair of ASM this year. The von Kármán Lectureship was named in honor of Theodore von Kármán. It showcases an individual in the field of astronautics who has made notable achievements and distinguished himself or herself technically. Our speaker tonight is Mr. Joe Crocker. As Vice President and General Manager of the Civil Space line of business for Lockheed Martin Space Systems Company, Mr. Crocker has executive responsibility for critical national space programs relating to human spaceflight and space science programs. These programs, some of them include the Orion Multipurpose Crew Vehicle, Hubble and Spitzer space telescopes, GOES-R weather satellites, and many, many years of missions to Mars. Jim began his career as a junior engineer working on Apollo 17, designing electronics for 3 crewed Skylab missions. This solidified his passion for space science and human spaceflight, or in AIAA jargon, this might be what Jim would call "when did you know" moment. Since then, he's had an exciting career across the space industry, holding senior positions at Ball Aerospace, the European Southern Observatory, Sloan Digital Sky Survey, the Center for Astrophysics, Johns Hopkins University, the Space Telescope Science Institute, and now since 2002, Lockheed Martin. In the area of astronomy and astrophysics, Jim is known for conceiving the idea and leading the team that developed COSTAR. This is the solution to the flawed optics of the Hubble Space Telescope back in the 1990s. He worked closely with the crew of STS-61 to develop on-orbit repair techniques and crew planning for the installation of COSTAR, which successfully restored Hubble's vision. If you have been to a presentation in Washington, D.C., where Senator Mikulski has spoken, she has often been known to say that our Hubble was fitted with a miraculous contact lens. Jim also led the system design effort of Hubble's Advanced Camera for Surveys. The addition of this instrument in 2002 improved the performance of the telescope exponentially. Jim played a major role in the design and construction of the largest astronomical observatory in the world, the Very Large Telescope in northern Chile, and served as project manager for the construction of Sloan Digital Sky Survey, considered to be the most scientifically important projects, one of the most, in astrophysics. Jim has participated and been involved with AIAA for many years, and we do congratulate you that this week you become an associate fellow. In addition to Jim's very amazing and stellar career, I have the personal pleasure of having opportunities to work with Jim in the area of supporting science education. And no one is more committed and passionate about serving the next generation for our workforce. His commitment is truly unwavering. He currently serves as the chairman of the board of the Denver Museum of Nature and Science, and I believe that the museum welcomes hundreds of thousands of the next generation every year. Jim received his Bachelor of Science in Electrical Engineering at Georgia Tech and his Master's in EE from the University of Alabama. And given this past Monday's football game, he has promised not to make any references to any other team's favorite. Tonight, Jim is going to speak on From Galileo to Hubble, Mankind's Extraordinary Journey, and it is my pleasure and honor to bring you to the podium, Jim.
Thank you, Mary. Thanks for that kind introduction. Well, good evening. It's really a privilege for me to be here tonight. You know, at the beginning of my third grade year, on a very chilly fall evening, my dad bundled the whole family up in our 49 Plymouth, and we drove off into the night. And my dad said something amazing. He said, "You're going to hear something truly amazing." Now, I could imagine seeing something truly amazing, but I couldn't imagine hearing something truly amazing. We pulled up to a small two-room museum and got out and went inside. And there was the biggest radio I'd ever seen in my life sitting on an oak table. I remember the tubes glowing, and I remember the size of it. And the name said Helicopter Super Skyrider. I had no idea what a Helicopter Super Skyrider was, but I was going to hear something amazing. There was a radio operator there who'd served in World War II who was running the shortwave radio. And he saw me. I was probably the youngest person there, and he motioned me over, and they had the receiver set up with a speaker, but he put these huge earphones on me. He said, "I want you to really hear this. You'll hear it first coming out of the noise, and then you'll start to hear it." And I couldn't imagine what I was going to hear. But then I heard it. And if you heard the sound, I could play it. You know it by heart. It was a beep, 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 beep. And I said, "What is this?" He said, "It's a sound coming from outer space. It's the first sounds to come from outer space." And as a matter of fact, that month, people from all over the world were tuning in on shortwave radio to hear Sputnik. And for me, in an AIAA moment, that was when I knew that space was talking to me. And I didn't quite understand exactly what was going on, but I knew at that time that I wanted to be part of this outer space exploration, this thing that was going on. And it wasn't just me. It was literally thousands of people, millions all over the world, who were enticed to go into science and engineering because they wanted to be part of this. Over the next decade, it didn't end. It kept on and on going. It wasn't just Sputnik. Yuri Gagarin was launched. And then, of course, several months later, John Glenn flew his single orbit, his 3 orbits around the Earth in Friendship 7. After that, the Gemini program started. And during this whole time, there was a whole generation of us, many of you in the room I see from that time, who wanted to be part of this. Well, I got to Marshall Space Flight Center right near the end. It was the last Apollo mission, but it was amazing just to be part of that little bit of history. You know, when you think about it, thousands of engineers from my generation went into space, but the majority of them didn't. The majority went on to explore and create cell phones, computers, CAT scanners, MRIs, new types of airplanes and aircraft. I mean, the list goes on, and we could think about it for a long time. But what that engendered in this nation, I think can be directly traced to the economic expansion that we have today. On the plane out here, I happen to be flipping through a recent issue of Aviation Week, and something caught my eye, and I'll just read it to you. It says, skills shortage. Aerospace sector grapples with the erosion of technology, engineering, and math training. Said the UK coalition government sees the manufacturing sector and the aerospace industry in particular as a means of lifting the country out of the economic doldrums and into a path of growth. But industry leaders are concerned that a lack of skills and perhaps more critically, interest in engineering from the up-and-coming generation of workers could starve the UK at a time when industry is finally getting the support it needs. Unintended consequences of exploration were, I think, what drove the economic engine of this country for a number of years. You know, we're at a critical time today in exploration and where we go from here in a number of areas, but I'd like to spend a few minutes tonight talking to you about exploration in perhaps the bigger sense, and in a different way maybe than you've thought about it before. And hopefully as we as a nation decide what our path forward is going to be in exploration, maybe it'll inform us a little bit and perhaps how to think about it. You know, I don't believe space exploration began with Sputnik or Apollo. I actually think it can be traced back to the first use of the telescope a little over 400 years ago now by Galileo. Now, why do I think that's the beginning of space exploration? It's because that's the first time a tool was used, something other than the unaided eye and the mind, to explore space. And Galileo did that, and he overturned 2,000 years of dogma, people say of the church, but actually of scientific dogma going back to Aristotle about what people believed about the universe and our place in it. And Galileo did that in a very brief period of time. He started in 1609 in the summer, made observations, and by the fall of 1610, he actually had written a publication called, translated from the Latin, The Starry Messenger. He said he constructed an instrument, and remember, he didn't create the telescope, he didn't invent it, but he did make one that was about 10 times better than anybody had ever envisioned, and 10 times better than what the parlor toy that was being circulated around Europe at the time was. Can you hear me okay? Is the echo too loud? Is it okay? Okay, that's great. So Galileo made a number of discoveries after he did this. He made something that took him 30 times closer. So it was the equivalent of having a spaceship and being able to fly up 30 times closer to the moon, 30 times closer to the planets, and to see things that had never been seen before. Now, one of the first things that Galileo saw was everywhere he looked, he saw stars. On a really good night at a really good site, you can see a few thousand stars. Everywhere he looked, he saw stars. He could see thousands of stars. And he realized right away that the galaxy was nothing more than just an innumerable collection of stars distributed in clusters. The second thing he saw, amazingly, was that the moon was another world. He could see mountains on the moon, and using trigonometry, he could calculate the height of those mountains from the shadows. He knew it was another world, a world that could be visited by humans, as you'll see later in a letter that he wrote to Kepler. He also saw that just like the moon had phases, Venus had phases, and he understood right away that that meant that Venus had to orbit the sun, not the Earth. He also saw sunspots on the sun, and he realized the sun and the moon weren't these perfect orbs like Aristotle thought, and in actuality they were physical objects, more akin to the Earth than to something else. But it was when he saw the moons of Jupiter that he was really sure that the Earth was the center, was not the center of the universe, and then in fact the sun was at the center and everything else orbited around that, because he saw that in the case of the moons of Jupiter that these moons that orbited around Jupiter were orbiting Jupiter clearly. He could see them night after night. He had a lot of time convincing people of that, but he changed our understanding of the universe, and quite frankly, for the next 250 years, everyone else just filled in the blanks. It was only in the middle of the 1800s, 1845 to be exact, that something as incredible happened again. You know, you probably haven't heard of the gigantic telescope that was built in Parsonstown in Ireland. You probably never heard of the third Earl of Roses, William Parsons, who was the astronomer who built this. And I can tell you that having built and been involved in some of the largest ground-based telescopes in the world, the last place you want to put one is in Ireland. That's probably not the place that you would choose to put a groundbreaking 1-meter class telescope that would actually be the largest telescope in the world until the middle part of the 20th century. But he did, and he did something amazing. He actually drew this picture. At the time, there was controversy about whether or not these nebulae, these whirly things that they saw in the sky, were nebula, gases that were forming solar systems, or, as William Parsons thought, he could see stars resolved in these nebula. He thought that these were stellar objects. And in fact, this was the first deep space object. This was the first galaxy that was ever observed. And Parsons observed 197 of those through his telescope. Now the problem is that when your seeing comes and goes, and you don't have photographic plates, and you have to draw what you see, he could see the individual stars, as he noted here. He believed these were actually stellar objects, unlike William Herschel, who believed that these, and other astronomers at the time, believed these were nebulous, gassy solar system formation. But in fact, from this Hubble Space Telescope image, we see that he had recorded the image of other galaxies. This would take another 100 years to be confirmed, and it would actually be Edwin Hubble who, using the Hooker 100-inch telescope, was able to prove that these were objects outside of our Milky Way, that these stellar objects were island universes. You know, most people remember Edwin Hubble from the expansion of the universe. What's often missed is the fact that using a technique that was developed by Henrietta Leavitt, a Harvard astronomer, of something called Cepheid variables. Cepheid variables are just stars that are supernovae that we know the brightness of. And if you know the brightness of something, you can tell the distance to it. It's like if you have a street lamp and you know it's a 100-watt bulb, you can calculate how far away you are from the street lamp merely by its brightness. What Hubble discovered was with these objects, these things that Parsons had seen were island universes. They were outside of our own galaxy, and that, in fact, the structure of the universe was an enormous number of these deep space objects like M51 that you see in this image. Now, everybody also knows that Hubble discovered the expansion of the universe. Basically, he did that by measuring with spectroscopy the fact that all the galaxies are moving apart. And the expansion of the universe was very controversial for a time, but we know now that Hubble was right. As a matter of fact, that's where we get the name for, I think, the next revolution that's occurred in astronomy, which is astronomy from space, using telescopes like the Hubble Space Telescope. You know, Hubble's really amazing. It was really Lyman Spitzer of Princeton University who was arguing since really the B-2 rocket experiments that the United States conducted after World War II, that getting above the atmosphere of the Earth would be revolutionary for a telescope and an observatory. Many people have likened it to being on the ground trying to study birds from the bottom of a swimming pool. The atmosphere distorts the image, and so consequently, when you can get above the atmosphere, you can get much sharper images. But I think one of the things that wasn't realized until we actually got Hubble up and flying is that it's more than the resolution. It's also the darkness of space. When you're looking through the atmosphere, even on the darkest night in the best sight, glows. And so in essence, it's like trying to look through the windshield of a car that has a film on it, and you're getting bright light from the sun, and it makes it very difficult to see outside the car. We've all experienced that. Hubble being above the atmosphere, above the glowing atmosphere, can see very, very dark objects. The other thing that's amazing about this extraordinary telescope is that it's also, the first time since Galileo, a time when space exploration and humans came back together. It's the ability to service the Hubble Space Telescope with astronauts that makes Hubble so powerful. It's not just the fact that Hubble is above the Earth's atmosphere. It's the fact that we can replace the instruments on Hubble as technology advances. I know many of you, being engineers, are probably early adopters, and you had one of the first digital cameras that came out. I know I threw mine away. I wish I'd have saved it. It's probably worth some money today. But those first cameras that came out were maybe 300 pixels. Today, you can buy, you get for free on your smartphone something that's 5 or 8 or 10 megapixel camera. The advantage that Hubble had was by bringing new instruments up to Hubble, we were basically able to create a new telescope every time we came up by putting more advanced instruments into Hubble and making the telescope a more powerful device. As Mary mentioned, I worked on the advanced camera for surveys, and one of the arguments that we had with ACS was it would make the telescope 1,000 times more powerful when it was installed than it was with the first generation of instruments on board, and that really proved true. And it proved through in this image. We could sit here tonight and go through thousands of beautiful images of Hubble. You know, they're on postage stamps, they're in schoolrooms, and they're really, truly art as well as science. But I really think that this particular image on the screen today may be the most profound image that humankind has to date ever taken. It's the Hubble Extreme Deep Field, completed in just last year in 2011. But it's an image that we've been working on for almost a decade, basically by taking the telescope and doing long exposures and adding them up. This is over a 2 million second exposure with the telescope added up. We can see deeper and deeper into the universe. As a matter of fact, Hubble, just like making a time exposure with a camera that we all might have, can see fainter and fainter objects as we expose longer and longer and longer. What's amazing to me about this image is that those aren't stars. Each star that you see in this image is a galaxy, and galaxies have on the order of 100 billion stars in each of them. In the first Hubble Deep Field, we could see about 5,000 galaxies. In the most recent Hubble Deep Field, it's over 10,000, and we know that there are more as we push the images back further and further. The furthest galaxy in this image, matter of fact, just released this past year by combining the wide field planetary camera with the ACS images, is so old that this image would represent a time when the universe was only about 3% of its current age, about 380 million years after the formation of the Big Bang. It's amazing to me that we can actually, with the Hubble Space Telescope, see, in essence, 97% of the universe, back to a time when the universe was really just starting to form and collect into galaxies. So with this idea, going back to Galileo, we're exploring not only space, but we're exploring space and time, and we're doing it from space, which seems pretty amazing to me when you think about it. The next step in this evolution is going to be the James Webb Space Telescope. Let's see if this is, let me try this again. Can you just cue that one up and see if we can get it to play? It worked before, it worked in practice, I can tell you. So the James Webb Space Telescope, which is currently being built by NASA, will be the follow-on to the Hubble Space Telescope. But instead of a 2.4 meter mirror, the James Webb Space Telescope has a mirror that's over 6 meters. Oh, that's Hubble again. Wrong. We'll get this right in just a second. And this telescope is very interesting. It's designed to operate very cold, a few tens of degrees above absolute zero. It's like an origami device. It has to fold up to be launched and then has to unfold. The mirrors are beryllium. It's the best material to use when the telescope's very cold. The sunshade that shields it both from the sun as well as the temperature from the sun, so it can get cold, is the size of a basketball court. The mirror is an interesting story. A couple of us who came up with the architecture for this telescope, actually in the back of the Goddard Auditorium, were building this out of some leftover paper plates and working on the folding concept for the telescope. But this telescope is going to do something very amazing. This is the near-infrared camera, which is out at the Lockheed Martin Advanced Technology Center in Palo Alto, California, undergoing final testing. That instrument will actually image the very first light from the very first stars that ignited in the universe after the Big Bang. The very first photons to travel in the universe from stars that formed after the Big Bang will be detected by that camera. It's going to go in another interesting place that in exploration we think is going to be pretty exciting. It's called a Lagrange point. As you can see, the L2 point that this telescope is going to is about 1 million miles beyond the Earth, beyond the Moon. And the interesting thing there about these Lagrange points is that they're gravity wells or gravity peaks, where if you put something there, you can orbit it or it will stay there. There are Lagrange points that are formed by the Earth-Moon system, and there are also these Lagrange points that are formed by the Sun-Earth system as well. This is a Sun-Earth Lagrange point, and it's a great place to put telescopes. As a matter of fact, there are currently 2 U.S. telescopes, 1 U.S. telescope there, WMAP, and 2 European telescopes there. And of course, this is where the James Webb Space Telescope is going to go as well. It's a great place to do astronomy from because you get away from the hot Earth, you get out to where the Earth is not like Hubble getting in your way every orbit as you go around. And we're going to do phenomenal science. We're going to do things there that really push back where we think the boundaries of science are. But let's talk about exploration for a minute. My son worked for IBM a few years ago, and they were involved with National Geographic in something called the Genome Project, where they were going and collecting genetic material from around the world and doing a database. And by looking at mutations in the DNA, they could basically track back and determine the history of the dispersion, exploration, if you will, of people around the world. And you could swab your cheek, and he gave me a little kit to swab your cheek, and you could trace the history of your ancestors back all the way back to 50,000 years ago, when the first modern humans, a band of a few hundred, probably at most, walked out of Africa. Now, the interesting thing there is that they had been in Africa for 150 to 200,000 years and hadn't left. You know, we're in Texas, and I remember President Bush said, exploration is written on the human heart, and he's right. But it's not written on every human heart. It's only written on the few who actually do go and explore. And it's only written in the hearts of the cultures that basically support that kind of exploration. Because as we'll see, most cultures really want to stay where they are. They really don't want to go and explore. It's only a few people, small number in this case, a few hundred, who walked out of Africa 50,000 years ago, and who, by the way, 85% or more of the world's population are directly related to those few hundred people who explored out of Africa. The interesting thing here is that they moved really quickly after they came out of Africa. Within a few thousand years, they were all the way into Europe and all the way down into Australia. With only 12,000 to 15,000 years ago, they had crossed the Bering Sea and gone all the way down to the tip of South America. They had explored all the way into Australia and to many of the oceanic islands. These are islands where you could see the next one from the one you were on, but they had populated all of those. Now, why did they stay in Africa so long? Well, I think this satellite picture shows the whole story. They had an impenetrable barrier to their exploration. It was the Sahara Desert. This is an area whose landmass rivals the United States. But if you look, it's believed they either came up the Nile or they came along the coast. It's also thought that at the time that perhaps it was wetter, but for whatever reason, they finally crossed this impenetrable barrier and populated the whole world in a very short period of time. Or sort of the whole world, because you see, the islands around Australia, New Oceania is sometimes called, you could see one island from the next, or perhaps sail a few hours or a day and see the next island. But beyond the Solomons, the islands were days, weeks apart. And for 2,000 years, no one ventured out. However, something happened about 2,500 years ago. A group of people showed up, we think from genetic information, somewhat controversial, from Taiwan or from the southern coast of China. And they came with something amazing. They came with a technology that did not exist before, at least in this group of people. And it's amazing because this is a picture of what the Pacific Ocean really looks like from space. Our maps basically blow up the size of the islands so you can see them. Basically, the Pacific is essentially a water world. There's nothing there. But what this group of people from Taiwan showed up with was a new piece of technology. It was a double-hulled ship with sails, ability to carry provisions that would allow you to sail on rougher seas for longer distances. Within a short period of time, only 2,000 years, they had explored the entire Pacific. They had populated Hawaii, Easter Island, and if you believe their mythology, they might have sailed as far as Antarctica. In a blink of an eye, they went from 10,000, 15,000 years of not being able to explore to, with a new piece of technology, opening up an entire new place to live, new place to exploit. And in fact, in 1760, when James Cook, the English explorer, sailed into Tahiti, he completed a 50,000-year journey out of Africa where explorers from England met up with our ancestors who had gotten to Tahiti and populated the entire Pacific because of a new piece of technology, changing the ability of humans to explore beyond the barrier that had kept them locked up for so many thousands of years. We have a new vehicle, just like that ship, that's going to take us beyond the barrier of low Earth orbit and beyond the barrier of the moon, and it's called the Orion Crew Exploration Vehicle. Right now, this spacecraft, which looks a lot in some ways like the Apollo capsule, and it does for a good reason, it's just physics, if you're going to the moon or you're going to Mars or you're going to deep space objects, you don't want to carry along wings and wheels. You basically want a spacecraft that's just like those Polynesian ships, exactly what you need for the job. And that's what the Orion spacecraft is going to do. It's in production right now. We're moving forward for an upcoming test flight. That's this vehicle's down at the Cape now, going through proof testing and final integration for our first unmanned test flight. And then later, when the spacecraft's completed, we'll do a test flight to somewhere in the vicinity of the moon. Now, we've been to the moon before, but where we want to go is just like everyone who explores. We want to go to some place we haven't been before. And when you dream, you really need to dream big. Small dreams, even when you achieve them, are small. Big dreams, even if you fail to achieve them, or fail to achieve them in the time that you set, big dreams do amazing things. It's like the dream of space exploration, where we really changed the whole direction of the nation in science and engineering back in the 60s. One of the missions that a number of people are envisioning is actually a mission to the Mars system. Now, it's very difficult to land on Mars, but we know that we could land on one of the moons of Mars, and this is a diagram showing a possible trip to the moon Deimos. Deimos is very interesting because just like our moon, it's in tidal lock, which means the same side always, of course, faces Mars, which would allow you to do teleoperation down to the planet's surface. And we know today that amazing things are being done with teleoperation. I have a friend at Johns Hopkins who actually does robotic surgery using a device called the Da Vinci. But he teaches surgery in other countries because you don't need to be in the room with the patient. Other people are there. As a matter of fact, if you go and look and see how a doctor does surgery with the Da Vinci, they're not in the room with the patient. They're next door. They don't want to be disturbed by all that noisy stuff going on when they're doing the robotic surgery. You might as well be around the world on the other side if you have good comm links. And the same thing could be true here. We could teleoperate down to the surface because we're very close and we have very small time delays to do that. Now, this might be a destination that we could potentially go to in the 2030s. And that would be a big dream that many people have had, to go to Mars. And you don't have to necessarily land on the first trip. I think going to a moon of Mars, we call that Red Rocks mission, would be a pretty phenomenal first step, and I think you would agree. But you need to not, that's a step along the way, but just like the Pacific Islanders took small steps before they took big ones, one of the things to do is use these Lagrange points, these places where if you put something, you can stay, to actually practice and do some exciting science. One mission that we proposed is called Farside. And on this one, we would hang out at a Lagrange point, which happens to be on the far side of the moon, and teleoperate down to the surface. It's a very interesting crater there called Aitken Basin, which is the deepest impact crater in the solar system. It goes down to the lunar mantle. Now we know that, we believe that the Earth and the moon system, the moon of the Earth, was formed by a Mars-sized object that impacted the Earth and knocked the moon out. That means that the mantle that's on the moon is the same mantle that's on the Earth. So in essence, we can't drill down, it's too deep to get to the mantle of the Earth. We can extract lunar mantle material and actually study the Earth by extracting material there as well. But beyond the Earth, and if you want to dream big, one of the things that you need to realize is since the 1990s, we've discovered over 800 planets. In the 1990s, when we corrected Hubble, one of the big discussions that we had is, are there really planets around other stars? Well, everybody assumed there was, but there was no evidence that they were. If you look with the Spitzer Space Telescope, you just see a blob when you look at other planets. When you look at Hubble, and if I had this image that would click up, we actually with Hubble have detected direct imaging. They're just points, but we've detected images of planets around other stars. And with the James Webb Space Telescope, we'll be able to do an even better job of that. But sometimes you have to see things. You don't have to run the image. Just go back to the presentation. Sometimes you have to see things for yourself before they really make an impact. I think it was the same thing with Galileo. People had to see for themselves what he was talking about before they could actually convince them. And to really do that, to make that next leap, we need to tell us, Webb will help us, but to actually do what we would all want to do, we need a telescope much larger than the 6.5 meter Webb telescope. We would need to build an observatory at a Lagrange point that was something on the order of 20 meters. That's really only about 2 or 3 times bigger than the James Webb. It's on the scale, however, that it could do something amazing. And that is, we could detect and characterize planets around other stars. We could detect clouds and oceans and life-supporting chemistry. And if we did that, and if we were able to, in fact, see planets out of thermal equilibrium with oxygen, the universe would be a different place. It would change for us in our thinking, I think, as much as it did after Galileo. I love quotes, and I'm a collector of quotes about space and aviation. Let me give you a couple. Neil Armstrong said, "Science has not yet mastered prophecy. We predict too much for the next year and far too little for the next 10. 1609, Kepler wrote a letter to Galileo and said, "Ships and sails proper for the heavenly air should be fashioned, and then there will also be people who do not shirk from the dreary vastness of space." 1609, already anticipating voyages. A time will come, Christopher Wren, the great architect, said, "A time will come when men will stretch out their eyes, they should see planets like our Earth." I'll skip this one in the interest of time, it's a little long. Flight, this one, I had to be careful here. I've spent a lot of time at Hopkins, so I'm picking on Hopkins astronomers. Flight by machines heavier than air is unpractical and insignificant, if not utterly impossible. Simon Newcomb, 1902, professor of mathematics and astronomy, Johns Hopkins. Notice it was only a few years later when Mary Parker, upon seeing the first airplane fly over Chicago, said, "We bowed our heads, and before the mystery of it all, then lifted our eyes with a new feeling in our souls that seemed to link us all in hope sprang eternal for the great new future of the world." There's no hope for the fanciful idea that reaching the moon because of insurmountable barriers, think Sahara, to escaping the Earth's gravity. F.D. Moulton, University of Chicago, astronomer, 1932. My favorite quote, shortly after the landing on the moon, is Arthur C. Clarke, who said, "If an elderly but distinguished scientist says that something is possible, he's almost certainly right. But if he says that something is impossible, he's very probably wrong." The image that's behind you is of a star cluster that Hubble took. And we now know, just from the last several months, that each of those stars that we see has at least a planet, if not several, around it. In fact, we now believe from Spitzer data that there are at least 100 billion planets in our galaxy alone, and of those, 17 billion are in the habitable zone, based on statistics from the Spitzer telescope that are just being released. Matter of fact, some of that data was just released last week. 17 billion planets in our galaxy alone that are in the habitable zone. Now, the habitable zone is a place where you're close enough to the star for liquid water to form. We know on Earth that any place we find liquid water, we find life. Is that true for these planets? I don't know, but there's 17 billion chances that there are, if not life, habitable worlds that exist in our solar system. But could we ever imagine going there? If you look on the web, you'll see artist renditions of spacecraft designed for interstellar flight. And this one I found very interesting. This was an idea for using nuclear fission, not fusion, but nuclear fusion, not fission, basically dropping 250 tritium or deuterium pea-sized pellets, illuminating them with a laser, and propulsing a vehicle. And if you could do that, you could actually reach the nearest stars in decades, not centuries, not thousands of years. And before you think that that's a fanciful idea, I can tell you that there's a thing called the National Ignition Facility at Lawrence Livermore, which is trying to demonstrate nuclear fusion as we speak. Now, will they be successful? I don't know. We've been trying to get this working for power generation here on Earth for 50 years, and it always seems to be 25 years in the future, but I think we think too narrowly. I think it would be poetic if the power that powers the stars powers the ships that ultimately take us to the stars. Because this is the way the sun shines, with nuclear fusion, not fission, but nuclear fusion. It powers the sun. And people are interested in it because it could solve our energy problems here on Earth. This could provide, theoretically, thousands of years of power source. But the interesting thing is it could also propel us to the stars. John Grunsfeld, who's the astronaut who did all the servicing, one of the astronauts who did a lot of the servicing on Hubble, who's now the associate administrator at NASA for science, likes to point out that this may be an easier problem than the energy problem, because what you're trying to do in these fusion reactors is contain it. And so all these complicated magnetic fields are designed to try and contain it. Well, in case of a rocket, you don't want to contain it. You actually want it to exhaust out the back. And so it could actually be easier to do that. But literally in Europe and the United States, billions of dollars are being spent to develop energy sources that, when they are, could one day be the civilization, our civilization's way to get off the planet. More so off the planet, but out of the solar system. How long will this take? Well, it won't happen tomorrow. But I remind you that cathedrals in Europe were built sometimes with 5 or 6 generations, usually in a family of architects, who never saw the completion of the cathedral. They saw it start, or they saw something in the middle, but it might have been 5 generations of architects later who actually completed it. But if you don't dream big, you won't take the small steps. You won't sail beyond that next island that you can see. You won't encourage people to go into science and engineering and to do the really hard things that will have unintended consequences, such as developing a new source of power that we need to stop global warming and to cleanly develop the power that we need. When I was in the 7th grade, I had a teacher named Mrs. Gill. And coming from a very small town, she tried to put some culture into us small town kids. And so she did that by playing classical music, but also by exposing us to art. And one of my favorite artists was the modern impressionist, Vincent van Gogh. And he did this image, Starry Nights. And of course, there are Hubble Space Telescope images that, in art imitating life, seem to evoke that starry night, and this is one of them. But as I was flipping through one of the art books and looking at a quote that Van Gogh had, I thought it was pretty amazing. He said, for my part, I know nothing with certainty, but the sight of the stars makes me dream. The sight of the stars makes me dream of all the things that will be accomplished not only in the next 20 years, but in the next 100. The only thing I think we should ask is, just like the few hundred people who walked out of Africa, to whom 85% of us on this planet today are directly related to, is our civilization, the one that we're part of, going to be the culture that encourages exploration and from whom all of those starfarers will be derived? Or we drop the baton and someone else lead the way? Think about that, and thanks for this opportunity to share with you tonight. Questions?
We probably have time for one or two questions. If anybody would like to ask a question. I mean, what an interesting, inspiring lecture. Any questions for anybody? If you can, either speak up loudly or use the mics. Okay? Anybody? Well, you know, as you started and you talked about your time, you must be the same vintage as me. I remember all those same things you remember. And I remember how exciting it's been to watch the space age unfold. It's been such a motivational thing for people of our generation. And now we have to set the motivation for the people of the next generation to carry this through.
You know, we really do. Neil deGrasse Tyson said something. I see hundreds of thousands of school children come through the Denver Museum of Nature and Science, and I have the opportunity to talk with a few of them. But I'm struck by something Neil deGrasse Tyson said, because he deals with a lot of people too. He said, you know, when I talk to school children, and I'll ask them, you know, do you want to be a scientist or an engineer so you can, you know, make an airplane 10% more fuel efficient? It's like, shh. But he says, would you like to be the first woman to step onto Mars? It's a totally different conversation and a totally different story. And I see it in both the elementary and high school students that we deal with. And I know that what we do in space exploration, what all of you do, both in aeronautics as well as in space exploration, makes a huge difference. So thank you for what you do.
Well, Jim, we have two things to present to you tonight. First, you weren't able to be at the Associate Fellows Dinner, which is a wonderful ceremony. And so first, we want to give you your certificate of being a new Associate Fellow at AIAA. We welcome you to the fellowship and look forward to your continued involvement in AIAA.
Thanks,
And then, of course, second, and even more importantly, we really thank you and want to award you as the von Kármán Lecturer this time. I think you provided an excellent and inspirational lecture, and we thank you very much for that. I'll see if I can put this on as an Olympic moment here. And we'll look here. And one with the certificate. And we have one here with the certificate as well. And we'll shake hands. A little further over, okay? Thank you so much.
Thanks. Thank you, Paul.
So this ends our evening tonight. What a wonderful end to this day. I also want to make sure that we all understand how much we appreciate Lockheed Martin, their sponsorship of this conference, and of course this wonderful lecture by Jim Crocker. Thanks so much. Have a nice time. Remember, their bus is going to Dallas's football stadium tonight if you want to go see the Cowboy Stadium tonight. Thank you very much.